Good afternoon. So we are here for the last session of labs concerning the software OSLO. Okay, and we're going to do something a little different today. Today's lab is not so much about the optics of a system, but rather how do you model tilts, or when you move or displace an object away from the optical axis. So it's more a lab on how to use certain tools within OSLO. Now, up till now, all the exercises that you have done had every element placed along the optical axis, right? And the only coordinate you worried about was what is the distance of the next element from this element. So what you might not have realized that you were doing is you were in fact using some kind of local coordinate system, because if you had an element here, you gave the thickness to the next surface. So let's say you said something like 10 millimeters, and that meant the next surface appeared 10 millimeters away. If you had another surface and you said 10, that 10 was measured from this surface, not from this surface, right? So in effect, you were measuring a distance always from the current surface to the next surface. Now, this works for many optical systems, since many optical systems will have one single linear optical axis. But if you have a system which has a mirror in it, and the mirror tilts the light, of course, the entire optical axis of the system is going to change. That's one thing. And secondly, even if I had a system where all my elements are supposed to lie on the same linear optical axis, it may be that while manufacturing this system, a lens doesn't go into the exact position that it should have gone into, and it's displaced from its position, or it's rotated. Right? Now, I want to study this rotation or displacement without affecting subsequent elements. So let's say I had a system as I've drawn here, which has 3 elements in it. It may be that element 1 and 3 are correctly positioned. Okay, it may be that they are correctly positioned. But element 2 is in the wrong place or has the wrong tilt. Now, I want to be able to place element 1 and element 3 correctly and move element 2, either move it, so I could move it in the x direction, move it in the y direction, move it out of the correct place in the z direction, but not move element 3. In your current techniques, if you said, let's say element 2 had a delta z error, so it should have been 10 millimeters from element 1, but instead it was 12 millimeters. So there's a 2 millimeter error. Element 3 is still 10 millimeters away from the original location of element 2. But if I just write 10 now, I've changed my system, because now the entire length is 22 millimeters, not 20. So in this case, you might say, well, I know it's 2, I'll adjust the next distance. But sometimes you want to study the effect of varying. So you may do a study where you say, let me vary the position of element 2. And I want element 3 to stay in the same place during this study. I don't want element 3 linked to the coordinate system of element 2. So, in order to study such cases, and they're very important, once you have a perfect optical design, or what looks like a perfect optical design, what people will do is run something called a Monte Carlo simulation. So, they'll put in all the maximum values of error for the tilts and positions of each element, and the Monte Carlo simulation will assign a random value that lies within the range for each element and see is the overall result acceptable. It may be that element 2 moves and element 3 moves in such a way they compensate an error. but some other element moves in such a way that it aggravates the error. So you need to see in all possible cases, do I still get an acceptable result? So we could do all that we did up till today, just assuming that the next element is placed this much distance from the first element, and we didn't look at tilt at all. Okay, so in today's class or today's lab exercises are all for you to understand tilt and how to achieve tilt. Okay, so it's it could be that you have a mirror, or even if you don't have a mirror, how do you tilt one element and not affect the others? Okay. So to do this, first we need to understand the coordinates that they use. There are 6 coordinates, 3 for tilt and 3 for decenter of the origin of your coordinate system. So the tilt angles are given as TLA, TLB, TLC, and as shown in this figure, TLA is when the optical element rotates about the x-axis. So the x-axis is here, right? And so the element is rotating in the plane orthogonal to that. That is TLA. TLB is similar, it's about the y-axis however, and TLC is about the z-axis. That's typically our optical system. Okay, both this and this are left-handed tilts, whereas TLC is a right-handed. Okay, so I can tilt any element, and if I'm doing so, I'm doing so by using any combination of these 3 angles, or I could displace the entire origin of that surface, and then the displacements are dcx, dcy, dcz, each one of course a displacement along that respective axis. Okay. Now there are 3 sets of coordinate systems that you need to get acquainted with to be able to do what I said our goal was. So the first, well, it's not the first, but one of them is called the global system. We have not been using the global system. The global system, as the name suggests, will assign, or you will assign, one surface as your global reference surface. Any tilt or any decenter, any distance will be measured from that global surface. So this is not, you've been using local coordinates. You were always saying from this position a distance of so much, from this position a distance of so much, right? The global coordinate system is always with respect to a reference surface. So in the example I gave just now, if I said we had 3 surfaces, in the local we said this is a distance of 10, surface 2 is a distance of 10 millimeters from surface 1, surface 3 is another distance of 10. In global we would say this is 10 and this is 20, because if I gave the global reference as 1. I could say the global reference is 2. I can make any system my global reference. Then I might have some negative numbers to account for it. Okay, so I decide which is the global reference, but any measurement then is made from that reference point. Okay, so that's the global coordinate system. It's easy to understand. It's actually not the easiest system to use, because it's easier to make measurements along the optical axis. It's easier to make measurements with respect to the previous surface. Okay, so that's why the default coordinate system that you have been using, though you might have been not aware of it, is the local coordinate system. Now, if you look at these 2 figures over here, the dashed line shows you the y and z axes of some element. So there's some element that you can't see the x-axis, that variation that's sticking out of the board, but this is showing you the coordinate system that is used. The dashed lines show you the coordinate system of the local setting. You could displace and tilt that surface, and the displaced tilted version is shown here. So let me use another color. So this is a displaced tilted. So whatever surface was here has been displaced along the y-axis and tilted, and now is showing like this. Okay, I can now say the next surface will be 10 millimeters away from this surface, If I use the local coordinate system, this is the local, let's say this is surface 1. If I'm using local coordinate system and I say surface 2 is 10 millimeters away, it's going to be 10 millimeters like this. Okay. I could, on the other hand, say I won't use the local coordinate, I will use the base coordinate, and then surface 2 is going to be 10 millimeters away like this. Is that clear? So I have the global, that's fairly easy. Some surface gets designated as the reference, every measurement is made from there. Or I have the local, so I have a surface and its untilted, undecentered coordinate system is the coordinate system I make my measurement from for the next surface. Or I can say I have a surface and it's tilted and decentered, and its tilted decentered coordinate system acts as the coordinate system from which I define the location of the next location and orientation of the next surface. These are the 3 coordinate systems you need to be familiar with. Okay? And as we go along, you will understand why it's important to have local and base. I can achieve everything using both local and base or the global coordinate system. Okay. Now, one thing that may not initially be apparent, but on some thought should be clear, tilt and decenter are non-commutative operations. So, if you tilt first and then decenter, or you do the operations in reverse, so you decenter first and then tilt, you don't end up with the same system. And that's an example that is actually given over here. So, if you look at these 2 figures, both have the same tilt dcy and both have the same, decenter dcy and the same tilt TLA. Okay, but in this figure, the decenter was carried out first and then the tilt was carried out. And in this second figure, the reverse was done, and you can see the end result is not the same, right? So you need to tell OSLO which order you want to do an operation. So if you will see there's a certain screen, you can enter the coordinates. So for that surface, what do you want to do with that surface? It may be that you want to both tilt and decenter that surface. Then you need to tell OSLO the order in which those operations need to be carried out. So if you were writing programming, you would use the command dt1. You would use the command dt1. That means decenter first, tilt next, and if dt is equal to -1, it means tilt first, decenter next. Okay? Okay. Now, you also need to tell OSLO, say you have a surface and you tilt that surface. Now, you need to tell OSLO, and I give you an example of the difference here. So here I have a system, and there may be not very clear, but there is one lens here and there's a second lens here. Okay, and there's a mirror here. So in this case, tilt and bend option has been given as yes. So this is the coordinate window. You're going to see that soon. And you can see over here, you have chosen tilt and bend yes. Okay. In the same system, if I had chosen tilt and bend no, because there's a mirror here, the light has to obey the law of reflection. But I don't necessarily need to put my components in that direction, right? So the components have followed just where the angle took them, the natural theta. Say this is a local coordinate system. So you can see it says it's local. So I said theta, and these are placed at an angle theta, right? So this element, this angle is theta, this angle is 2 theta, right? So these elements are placed along the optical axis given by the local coordinate system following the tilt theta, whereas the rays of light are following the law of reflection, and therefore they bend 2 theta from the mirror. Okay. So again, depending on what I want to study, I might say actually carry out a tilt and bend or don't carry out a tilt and bend. Okay, and again you'll see why you might think I would always want to tilt and bend. But again we'll see where there may be cases you don't want to tilt. Okay. Now, if I have different surfaces and I at one surface enter some coordinates which causes a tilt and a decenter or any one of those operations, I now need to decide, does the next surface follow the local coordinate system of this surface or not? And I must have some way of telling OSLO, please follow this new tilted decentered coordinate system, or please follow some other coordinate system. Okay, maybe the untilted, undecentered. So the operation that carries that out is called the coordinate return. So again, you have this window over here. This is the coordinate window. This window you will open from the special column. Okay, and you can see your coordinates are local. In this case, tilt and bend is no, but there's a option here, coordinate return, and in this case it's chosen as no. Now let's look at what that means. We're using the local coordinate system and we have a series of elements. Okay, so they're showing you this is the starting one, and then there are 5 different elements. Element 3 has been displaced and tilted. And because you're using the local coordinates, element 4 now follows the new z axis of element 3. So all the subsequent elements, in this case elements 4 and 5 or surfaces 4 and 5, they lie along the newly defined coordinate system which has been defined by the new position of surface 3. Okay, no coordinate return was carried out here. Okay. If you carry out a coordinate return and you go to the untilted, undisplaced coordinate system of element 3 or surface 3, so elements, or rather surfaces 4 and 5, they continue along this original path. So you should be able to see the difference over here. In the upper figure, no return to coordinate has been done. So the surfaces 4 and 5 follow the original coordinate system of surface 3. In the lower figure, a return to coordinates, that's at RCO command, has been carried out, and therefore surfaces 4 and 5, they are along the original optic axis. Okay. And if you were to look at the coordinate system, coordinate data, you can see your coordinates are local and there's a coordinate return, and even here you have the option of saying return to coordinates, don't use the current local coordinates, return to coordinates, and I can say which surface coordinates I return to. Now I cannot, this was surface 3 that had all of these displacements and tilt. So when we say return to coordinates, you can return either to the original coordinates of surface 3, that is what is shown here, return to, so this is what will come up as your default option, but you could also choose surface 2 or surface 1. You can choose any earlier surface to return to. Clearly cannot choose a later surface to return to. Okay, and say you had put return to surface 2 over here. Now, what coordinate system of surface 2 should you return to? Should you return to surface 2's local coordinate system or its base coordinate system? Because it may have been tilted or moved. So the lower line says use the base coordinate system when anyone is returned to this surface, use the base or local coordinate system of this surface as the returned coordinate system. Okay, so I know it's a lot to take in. I'm running through it now. You're going to have all this information in the file that you have, and so you can work through it slowly. Okay, so the key points to take away: you have 3 coordinate systems: global, local, and base. You've been working with local so far. We are going to in today's class, do exercises that help you get to know the global system better, as well as the local and base systems better. Okay. So let's say we wanted to tilt a single element. So in this figure over here, so this is actually an exercise you're going to work through in today's class. If you look at this figure here, it's similar to what I had shown earlier. You have 2 surfaces. So this is one lens, and you have another lens, and you have a mirror. Okay. Now let's say I want to tilt this mirror such that this beam scans, the beam moves, but lens 2 stays in place. Where would you need this? Say you're using a beam of light to scan something. The optics is all stationary after the mirror, but you're moving the mirror, and maybe you have a lens to focus a spot, and that focus spot has to move around in a straight line, right? So I need lens 2 to stay in place. If lens 2 is linked to the coordinate system of the mirror, every time the mirror moves, lens 2 is going to move. So I can't link it to its local coordinate system. I have to set up the system such that I can tilt the mirror without moving the lens. Okay, so if you look at this setup, I've just put 2 lenses. This is the image is from this spreadsheet over here, and now we want to set it up so that we can move the mirror without moving the second lens. Okay, so here's a sequence of operations. There are many different ways of doing it. Okay, and I've given you 2 different methods in the write-up that you have. This is one method using local coordinates. The other method is using global coordinates. Personally, I find this easier, but you're free to use any system that you want. And I thought running through it together would make it a little easier. Okay, so we want to tilt the mirror, and the mirror happens to be the 3rd surface of our system. Okay, so what are the different things that we need to do? We need to set up the mirror with a tilt of 45 degrees and the tilt and bend option on. So if I go to the coordinate window, I'm going to set up 45 degrees and the tilt and bend option is on. Okay, then I'm going to cheat. I want to tilt, but I don't want to change the optical system. So I actually add what's called a dummy surface. It's called a dummy surface because optically that surface plays no role in the system. You're putting it in the system to work around the coordinate system. Okay, so you're putting in a surface so that you can play around with the coordinates. In an actual system, there you wouldn't have an extra surface in there. Okay, so it's only there to help you play around with the coordinates. So you add a dummy surface. Okay, so if you look at the previous, oh, I don't have that screenshot. You have now this extra row. It doesn't change your optical system. If you look at your optical system, it's exactly the same because I've inserted a row. There's no power, there's no thickness, so this doesn't change anything in your system. I, however, need to transfer this thickness onto this because I want this surface is just going to add as giving me that extra thickness, and then I'm going to change something in the coordinates of surface 3. Okay, so I need to transfer the thickness of surface 3 to the new surface 4. Okay, and that's what this screenshot shows you. Now all I've done is transfer the thickness. My diagram still doesn't change because I haven't changed anything in the optics, and surface 4 lies exactly on surface 3 at the moment. So if I were to look at the optical system at this point, you wouldn't be able to tell any difference. Okay, I haven't done anything with the coordinates yet. Now I will set up this by tilting surface 3 by 45 degrees, okay? And we put tilt and bend on, that ensure that both the optics as well as the light follow the same path. Now let's go back to surface 3, remove the tilt and bend option, okay? Put a coordinate return on. The moment you remove the tilt and bend option, you're going to see your optics goes haywire, okay? So don't be alarmed when you're working with coordinates if during the process of setting up the coordinates, an element seems to go and sit in completely the wrong place, okay? This element should have been somewhere here, but I've removed the tilt and bend and it's gone to some crazy location, okay? I now add and double the tilt angle. So I had 45 originally, I add 90 over here to surface 4, and that brings it back now to the right location. Okay. Now, what is the whole purpose of doing this? The whole purpose is to create two surfaces. One surface is doing the optics and one surface is allowing me to manipulate the coordinates. And manipulate the coordinates in such a way that we should be able to tilt this mirror and move the beam here, translate the beam here, and this stays in place while this lens stays in place. Okay, so let's just try to do this. Okay, so I've entered all the numbers of the example. What I haven't done is so the coordinates is, you go to the special column, surface 3 coordinates, and I'm going to enter tilt of 45 degrees, and I want tilt and bend on, and I say yes, okay? And I also want to see this last surface, okay. I now want to add a dummy surface, so I'm going to insert a dummy surface, and I will do what I just said. So we'll make this 0 and we'll make this minus 30. Your optical system shouldn't change at all, right? When we are using a mirror, in the glass type, you go here and choose reflect, okay? And you need to tell OSLO, I am interested in tracing the rays after the mirror, because I can have a partially reflecting mirror and the light could go through. So OSLO is not going to assume you want to look at the reflected light. So in order to tell the software you're interested in the reflected light, all thicknesses after the mirror need to be negative. Okay, so that's why I put minus 30 over here. Okay. Okay, I've added a dummy surface, I've transferred the thickness, and now I'll go back to surface 3 coordinates and I will remove the tilt and bend, okay. I still have 45 degree angle over here, and now one other difference is I'm going to say that change the coordinate return, make it yes, and I'm going to say return to that surface 3 itself, but the untilted coordinates. Okay. Now, since I've done that, I'm in the process of setting up my system. This has the wrong location. So I'm going to go now to the coordinates of surface 4 and give it a 90 degree tilt. Okay. Why? Because this is a 90 degree tilt with respect to the untilted coordinate system of surface 3. Okay. So if I would have had my elements like this, now I have an actual 90 degree tilt. Okay. Surface 4 should be clear to you now. Surface 4 is linked to the untilted, undisplaced coordinates of surface 3, right? So now if I change surface 3, surface 4 continues to remain linked to the untilted, undisplaced. Therefore, I can do anything to surface 3 now and it should not affect surface 4. Okay, this is where you have famous last words, and now I will tilt surface 3 and everything will go all over the place. So let's see if it works. Okay, so how do I want to do this tilting? I want to tilt surface 3. Best way is to put a slider wheel design. Let's put surface 3. What's the parameter of interest? It's the tilt of surface 3, right? So I have now a slider wheel, and thank goodness, if I move surface 3 now, you can see surface 4 is not changing, right? Okay, this is more or less the exercise that you have to, one of the exercises you have to work out for today's class. But you can see the idea is, how do I control tilt, and how to not only control tilt but control it independently of the other surfaces. Okay, in this example all we've done is tilt, but of course I could set it up so that I am doing the same thing for displacement, and even if I displace something, surface 4 is not going to change. It's set up with respect to the untilted, undisplaced coordinate system of surface 3. Okay? Okay. So I hope with that brief introduction you have a better understanding of the coordinate systems available in OSLO, right? And this is just a very brief introduction. There are a lot of different things you can do. And as I said in the document given to you for today's class, there are 2 methods by which to achieve this tilting without displacing or tilting the subsequent elements. That is not to say those are the only 2 methods. You may come up with some other method. There are, depending on how you play around with all the different options available. Okay, so I would suggest there again were 2 documents for you to go through today. So please go through them and work through the different exercises. His question is, why can't I do the same thing without surface 4 and just say the surface after surface 3 returns to the untilted version of surface 3? If you didn't have a mirror, you could do that easily. Because you have a mirror, you also want to say, do I do tilt and bend or not? There's an extra variable that comes into play there. You're right, you don't need the dummy surface if you were not having the surface that was being displaced or tilted was a mirror. If it wasn't a mirror, then you wouldn't need that. You can try, there may be some combination that allows you to do that, but my intuition is that because you also are saying the light goes for 2 theta, I'm giving theta but the light goes 2 theta, this extra variable it makes it easier with the dummy surface to take all these different things into account. But you do not need a dummy surface if in the example in the PowerPoint, I had a sequence of elements and one element was moved out and the rest were back. There is no need of a dummy surface there. Then I'll say just go back to the coordinate system of the undisplaced surface. The dummy surface is only because I have a mirror here.